Hello, this is FlippedHarber for Precalculus. In this video we're going to cover the dot product for vectors. The objectives for this lesson are to find the dot product of two vectors, find the angle between two vectors, put a vector form in magnitude and direction, determine whether two vectors are parallel, determine whether two vectors are orthogonal, decompose a vector into two orthogonal vectors, and compute work. The outline for this video, we'll start with the dot product. We'll talk about finding the dot product. We'll talk about some properties of the dot product. We'll talk about a theorem for finding the angle between vectors. We'll talk about the vector in magnitude and direction form, parallel vectors, orthogonal vectors, something called the projection of one vector onto another, and then we'll end with work. Now the dot product is one of two things that we can do to quote-unquote multiply two vectors. Now I've got two vectors here, v and w. They are in ij form. We have v is equal to a1i plus b1j. W is equal to a2i plus b2j. Notice the bars over v and w, that tells you that they're vectors. Remember, we can put a bar over vectors instead of trying to make them bold text. The I and j have these fancy cute little hat things over them. They're kind of a special notation that shows that they're not just vectors, but they are unit vectors. So the way that we find the dot product is we're actually going to do something with those components a and b from each vector. So v dot w is simply equal to a1 times a2 plus b1 times b2. So this creates a scalar product. That is, we're taking two vectors, we're multiplying them together, and the result will be a scalar, a non-vector number. So the dot product, since it always creates a scalar, is sometimes referred to as the scalar product. So if you ever hear the term scalar product, it's just another way of saying the dot product. So let's go ahead, take v and w equal to these two vectors, and actually find the dot product. So v dot w is equal to 2 times 3 plus 3 times negative 4. So v dot w is equal to 6 plus a negative 12, which is equal to a negative 6. A dot product is always going to create just a scalar number. Now here's some properties of dot products. A lot of these are going to seem very familiar because they behave in similar ways to multiplying numbers. First of all, the dot product is commutative, which means that we can take v dot w, it's equal to w dot v. The dot product, or scalar product, is also distributive. If we take a vector and dot product it, dot it with a sum of two vectors, we can do the dot product separately. Now when we have some scalars involved, so c1 times the vector v, so that's a scalar times the vector, times, dot c2w, so there's another scalar that's multiplying w, we can do the dot product and multiply by the product of those two scalars. So c1, c2 means that we can multiply those two scalars and then multiply that together into the dot product. Oh, and that should be a v and w, not a u and v. Oh well, that's what you get when you copy and paste, I guess. If you take a vector and dot it with itself, v dot v, you're going to get the magnitude of v squared. When you take a 0 vector, and the 0 vector is 0i plus 0j, when you dot it with the vector, you will always get 0. Now notice that second 0 doesn't have the bar on it. The 0 in the front is a vector, which means that it's 0i plus 0j. The 0 at the end is not a vector, so it doesn't have the bar over it. Okay, so let's talk about a theorem for finding the angle between vectors. Now this is useful because vectors are all about magnitude and direction. So being able to talk about how two vectors are related in direction is a lot of times very, very useful in physics and other sciences. So the angle between these two vectors, obviously it's going to use the dot product because it's in this section. We have an equation that says the cosine of theta, now that would be the angle between them as you see in the picture, is equal to u dot v. Now since the dot product is commutative, whether you go u dot v or v dot u does not matter, over the product of their magnitudes. So we take the magnitude of u and multiply it times the magnitude of v. So the dot product is going to create a scalar. It's going to create a plain old number. On the bottom, the two magnitudes are plain old numbers. They're actually plain old positive numbers. So the cosine of theta is equal to this ratio, which means when I want to actually find theta, what I need to do is take the cosine inverse of this stuff. So of u dot v divided by the product of the magnitudes. And that will find the angle between the two vectors. Now let's go ahead and find the angle between these two vectors. Now I have set these vectors up so they're pretty nice. If we find the magnitude of v, remember the magnitude is really just an application of Pythagorean's theorem. That's going to be the square root of 3 squared plus negative 4 squared. So you should be noticing that this is equal to the square root of 25, which is 5. Now, I'm going to go ahead and give it away. Look at the two numbers, 3, 4. Take the hypotenuse, that's a 3, 4, 5 triangle. And I've done the same thing with W. W is also a 3, 4, 5 triangle, but obviously we've got different order for the numbers. Magnitude is still 5. So we're going to find the angle between these using our new equation. Let's go ahead and find the dot product divided by the magnitudes, and then we'll take the cosine inverse after we found that. So we're going to take v dot w, so we're going to go 3 times 4 plus negative 4 times negative 3, so that's our v dot w on the top, divided by 5 times 5, our two magnitudes. Both v and w have a magnitude of 5. So on the top we have 12 plus 12, we have 24. On the bottom we have 25. So in order to find the angle between them, all I need to do is take the cosine inverse of 24/25. Now, that's not something you're going to find on your trig table. So plug it into your calculator. That's approximately 16.3 degrees. Okay. So let's go on and talk about a new form for the vector, and it's referred to as a magnitude and direction form. But if you look real close, boy, that kind of looks like something. This stuff right here, what does that look like? Well, it looks a lot like the polar form for points and things that we've talked about. And really that's all it is. It's the polar form, and that's why it's in this chapter. It's in this grouped in with all this stuff about polar form. This is really just the polar form. We've done this already. We're just applying it differently. So we think about the A and the B as an X term and a Y term. The magnitude of V is that radius. It's that distance from the center. So finding that magnitude of V, we've seen it, we've done it, we love it. It's Pythagorean's theorem. That cosine theta and sine theta, those two thetas are always the same. And we're going to find them basically the way we've always been finding them. What I can do to find theta is take the cosine inverse of my A value, now think about that as my X, divided by my magnitude. That magnitude, again, is the radius, basically, from polar form. So this is not anything new. We're just applying it to this new idea of vectors. Now, let's go ahead and put V from earlier into polar form. So V, again, was 4I minus 3j, excuse me. So we're going to put this into this new magnitude direction form, which is really just polar form. I'm going to find my magnitude the exact same way. We've already actually found it. My magnitude is equal to 5. My angle theta is equal to the cosine inverse of 4/5. So find that theta, use your calculator because you're not going to be able to look that up on your table. You've got your angle, and then you go ahead and put it into magnitude form. Pretty straightforward. We've done this a lot. We're just now doing it for vectors. Now, parallel vectors. Obviously, two vectors are parallel if the angle between them is 0. So if the angle is 0, that means that when we take the cosine of that angle, we're going to get 1. So really what that means is that V dot W divided by the two magnitudes equals 1. If they ask if two vectors are parallel, you need to take this product, divide by the magnitudes, and see if you get 1. If you get 1, then yes, those are parallel. Okay. Now, orthogonal vectors. Orthogonal is just a fancy word that means perpendicular. So don't think orthogonal, just think perpendicular. Okay, that's all it means, perpendicular. So when we take the dot product and we get 0, that means that these two vectors are orthogonal. So if they ask you, are these two vectors orthogonal? Are they perpendicular? If you take the dot product and you get 0, then yes, they are perpendicular. Now, this is probably going to be the most complicated idea from this section, the idea of a projection. Now, the math is not difficult. The idea is a little bit troubling. So, I have two vectors, V and W. Now, a projection onto W, I like to think about it like a shadow. If we put the sun up here, straight above W, so the sun's up here, and V casts a shadow. So I'm going to draw a perpendicular line. This is a perpendicular line to W. Here is V's shadow. Okay, that is what we're finding, is we're finding a projection of V onto W. Or if you want to think about it this way, it's V's shadow on W. So our notation, the projection onto W of vector V. Okay, so the small subnotation is the vector that the shadow is being cast on, and V is what's leaving a shadow on W, is equal to V dot W, hey, makes sense that it's the dot product, V dot W, divided by the magnitude of W squared. Okay, not the magnitude of W, but the magnitude squared. Probably a very common mistake is to forget to square that number. Now all of this is a scalar that we then multiply times the vector W. So that is the projection of V onto W. So it is a vector. Notice it's got a direction. It's got a magnitude. It is a new vector that is parallel to W. Okay, it points in the exact same direction as W. It's possible for it to point in the opposite direction, but in our picture, that vector points in the same direction as W. Now, this is probably going to start to look familiar to my physics students. Okay, what we're doing is we're finding components of V here. A component is a piece of a vector. Okay, we can always break vectors into pieces, and when these pieces point in the same direction, it makes things very nice. This stuff is huge in physics. Okay, not necessarily high school physics, but this stuff is huge in physics. So we're going to label this new vector, this projection that we just found, as V1. Okay, it is a vector. Okay, so it gets that bar over it. It is a new vector that is parallel to W. We are also going to find the vector that is perpendicular to W. Now I've drawn it in here kind of as a dotted line. Let's draw it in here as a vector. So this new vector we're going to call V2. It's perpendicular to W, and it's really super easy because all the work's been done up here finding the projection. So V2 is equal to V minus V1. So that's really super easy. You just take the two components, A and B, and subtract them. So this is what's referred to as components. We have a component parallel to W, that's the projection, and we have a component that's perpendicular to W, that's that V2. So you're going to be asked to do this as well. Now, our last topic is work. Now, work is a concept in physics. It's a number in physics that represents changing the energy on an object. Okay? Again, this is going to feel very familiar to people in physics, but the way it fits in for us is work is a dot product. It's a dot product of a force vector. Notice it's a vector because it has a bar on it. So F is there for force. So it's going to have an A and a B component, an I and a J component if you want to call it that. And we dot that with a direction vector. So this AB vector is the direction that the object is moving. Now, if an object is moving straight left or straight right, straight up or straight down. These direction vectors are very, very simple. If an object is moving to the right, then the vector is just simply I. And then if it moves 5 feet or 5 meters to the right, then it would be something like 5I. So that AB vector is usually very easy because things use straight left, straight right, straight up, straight down. So for example, if an object is moving to the right 5 feet or 5 meters, that direction vector is 5I. Okay, so that's it. It's time for you to try some of this stuff on your own. I'll see you in class, and I will see you online.